Hello and welcome back to our second track here. We're just going to jump right in so that we keep everybody on schedule. So we hope you're looking forward to the tech track. This is featuring innovations from batteries to AI to rocket thrusters and everything in between. If you didn't join us earlier for the life sciences track, I want to redirect your attention over to the right-hand side of your screen. There's a Q&A module over there where you can post in questions or upvote questions that other people have posted. You can also feel free to use the chat to talk amongst yourselves. If we don't have time to answer any of your questions here, we are happy to take those offline and send you responses in time. The session's on a short delay, so please post your questions immediately as soon as you think of them, and don't wait until the end. So with that, I think we will just kick it off with our first presenter for the tech track, Professor Bruce Koel from the Department of Chemical and Biological Engineering, and he will be presenting a cost-effective and environmentally friendly way to recycle lithium-ion batteries. Take it away, Bruce.
Hi, good afternoon. I'm very happy to have this opportunity to introduce you to our company, P&E, or Princeton New Energy. P&E is an innovative clean tech startup spun out of Princeton in 2019. With extensive battery recycling research and development experience, our mission is to deliver a cost-efficient lithium-ion battery recycling solution that makes it profitable and sustainable to recycle lithium-ion batteries anywhere. Our technology is a novel plasma-based direct lithium recycling process, and we have a small hard-hitting team in place that I'll introduce you just to the founders on the next slide. Chao Yan is the Chief Executive Officer, Shofan Yang is the Chief Technology Officer, and Professor Yiguang Zhu and I serve as technical advisors. The demand for recycling lithium-ion batteries is due to three main reasons resulting from global electrification: increased sustainability by recycling manufacturing scrap and dead batteries, increase access to strategic metals such as cobalt used in batteries, and develop a much greener and efficient direct recycling process that does not involve pyrolysis or acid leaching. On the right, you can see the predicted growth over the next decade in electric vehicle sales, lithium-ion battery demand, and used battery waste driving this development. The market size for battery recycling is predicted to grow from $2 billion to $27 billion in 2030. VC investment in battery recycling is focused now on early stage startups, and in 2021 put $757 million into battery recycling companies. This is the hottest topic in venture capital trend in the market. Compared to developments in lithium-ion batteries, recycling is really lagging. Current processes are from mining technologies. Pyro uses high temperature to smelt the aged batteries, while hydro uses strong acid to leach out the key elements as shown on the left. These processes furnish raw materials that need to be transported to a manufacturing plant to completely remake the cathode materials. On the right is our process. Some steps are the same, but we've developed a game-changing technology with many innovations for these steps as well, but importantly, based on a novel plasma purification step that enables the aged cathode materials to be recovered, retaining most of their structure and composition so they can be directly regenerated as a product of our process and available for use as battery-grade cathode materials. This is a comparison of P&E with the most active recycling companies today. The top row shows that P&E direct recycling checks all of the boxes that are desirable. On2 technology is also promoting a direct recycling process, but appears to be not as high performing. The other two companies rely either on pyro or hydro and do not compete as well. Our technical results demonstrate a very good quality of our regenerated materials based on our kilogram per batch lab scale processing. The left table lists some of the characterizations that we do, which shows that regenerated LCO materials in this case, which is a type of lithium-ion battery, have very high purity, good particle size distribution, and high capacity. On the right, NCA materials, a different type of battery, shows good morphology and crystallinity and the effectiveness of our P&E method for removing fluorine impurities which accumulate when the battery is manufactured and which can't be removed by regular solvents commonly used. And importantly, in a coin cell battery test made with our recycled material, kind of in the center there with 2 crossing lines, they have identical performance as new commercial material. This is analysis that was conducted by Argonne National Laboratories using their life cycle analysis model for the NMC 532 lithium-ion battery. Producing cathode materials by mining, labeled here as virgin, is shown as the tall dark blue bars as reference, and the green bars, smaller ones, are for the P&E direct process. Their analysis shows on the left a summary of the large reduction in cost per kilogram of cathode produced by P&E, and on the right shows the huge environmental impact that our process would make compared to mining. Our business model is equipment licensing and service over the short term, and over the medium term, developing into manufacturing applications. This has been a really exciting year. In research, we formed collaborations with all of these entities and labs shown on the left. We're the only direct recycling company awarded a Department of Energy Small Business Innovation research phase 2 funding of $1.15 million. And we're now busy talking with investors to raise capital, and importantly signed a joint pilot partnership agreement last summer with Wistran and ETAC. Now I'd like to share a short video showing the major processing step of our lab scale capacity demonstration so far. Okay, thanks for your attention. I can now answer questions.
Thank you very much, Bruce. It's great to see how you've really embodied the transition here from the laboratory discoveries into the commercial realm. I mean, can you talk a little bit more about how it's been now that it's moved out of the university?
So yes, the movie illustrated a sort of kilogram per batch processing stage. Importantly, though, I'd like to share this slide announcing a joint pilot partnership from July 2021 with Wistron GreenTech and ETAC worldwide. And we're building a recycling line to take this to the truly pilot scale. That's going to be available hopefully during 2022. We're using an available manufacturing line in Wistron's factory in Dallas. It's being built now. The equipment's in hand. And Q1 of 2022, we're aiming for 120 tons per year type capacity. We won't run it for a year, but we'll generate it at that scale. And then in Q3, if everything goes well, we'll move on to a 500 tons per year scale, and perhaps scale up after that if we're in good shape. I just want to mention that also a strategy for us was to focus initially on recycling batteries from electronic devices. That takes advantage of Wistron's position, both in having used batteries and also being suppliers from things like iPhones and laptops from Apple, Dell, Lenovo. And later, if we're successful here, we've shown that our process works on all of these batteries that we've tested so far, and we should be able to move into the electric vehicle EV battery market, which is much larger, by forming new partnerships and suppliers. That will also need to be tested at pilot scale.
Excellent. I do have one quick question from the audience here. What waste materials are generated during your process, and how do you dispose of them?
That's a great question. My tendency would say that we produce a very small amount of waste. Some people would say no waste. We do recycle all of the any of the liquids and solids that are used in the production. We're likely to, of course, generate some waste, but compared to pyro and hydro, it's completely off the scale. So we generate very little. And any gas waste can be treated and released without any particular harmful effect.
Excellent. And with that, I think that's our time. And thank you very much, Bruce. Moving on to our next speaker, we will have Fatima Ebrahimi, who is a principal research physicist with the Princeton Plasma Physics Lab. And she will be presenting on a rocket thruster that could take humans to Mars and beyond. Take it away, Fatima.
Thank you, Chris. Do you hear me? Yes, good. So thank you everyone, and thanks for the opportunity. So I will talk about a propulsion technology. And the first question is that why? Why do we need a new propulsion technology? And the answer is that for any kind of transportation, speed and travel time and fuel efficiency are really critical, and that's also true for deep space travel. In particular, if you want to have a fusion moon base to deliver, supplies from low Earth orbit to moon, or asteroid mining, or planetary defense, and in general for space exploration to Mars and beyond, we really need high thrust electromagnetic propulsion with high velocities, high exhaust velocities of 10 to hundreds of kilometers per second. So how do we achieve this kind of exhaust velocity? And for that, we need to look at our sun, that particles with high velocity, hundreds to thousands of kilometers per second, are being ejected through a process we call magnetic reconnection, as is shown here. And usually in my research, I usually work on the problems that fusion and astrophysics actually overlap. And this thruster concept is really an example of it, that it originated from the fusion research in the National Spherical Tokamak experiment we have at PPPL at Princeton, but also the fundamental mechanism it's very similar to the process of solar flare, how it's generated. So to the left, you see the experiment at PPPL. It's a spherical tora, and as you see in the middle of it, there's not that much space to put magnets, and we usually put magnets to actually create current and confine our plasma for fusion. But we do have an experiment we call helicity injection experiment, that we put magnets under at the bottom of the device. And through that, as you see, through this movie to the left, we actually generate magnetic loops similar to the solar flares. And so this experiment, this generating these magnetic loops, led to several discoveries. And one of them was that when I was doing studying and analyzing the experiment here, noticed the generation of these distinct plasma bubble or plasmoids that distinctly they were generated during this experiment. And interestingly, they were also momentum carrying. So at that time, I kind of knew that these momentum carrying objects can be used for space propulsion. So that's how it started. So there is basically the combination of two processes. One is that generation of these loops to the left, that we knew it in fusion experiment. We always, since alpha time for several decades, we knew how to create these magnetic loops. But the invention here is that to actually combine it with a newer process or a new development that we understand theoretically and from the simulation by modeling how magnetic reconnection can produce these fast plasmoid objects that can be ejected from a point we call X point, and that's how the thruster or the rocket is going to be propelled forward. And you can imagine that this is really similar to the process that steadily, if you can see, blowing the bubble, so bubble steadily, you can actually form these bubbles, and form it and detach, and form it and detach. So this is very similar to blowing soap bubble, and that is the basic of it. And to the left, you see the schematic of this thruster. That it's really magnetic thruster. It means that usually for any kind of propulsion, you need convert some sort of energy to kinetic energy. Here is all based on magnetic reconnection, fast magnetic reconnection, converting the magnetic field to kinetic energy by forming this plasmoid object. And that is through the coils that we configured very carefully. And everything here is based on really state-of-the-art simulation, MHD simulation. So it's not projection. All of these really high velocity of 20 to hundreds of kilometers per second has been produced in the simulation, which you see in the movie to the left. And these blobs are generated and continuously can be repeatedly, trains of plasmoids can be generated. So, and the unique characteristic of this propulsion is that it's, since it's magnetic, so magnetic field is kind of a knob that you can adjust for how much you can have acceleration and how large your thrust can be. So it's powerful and efficient, and also it's flexible in terms of propellant, that it's hydrogen. It could be light atoms and also heavy propellant. But the important thing is that this concept has a firm scientific foundation based on the experiments that we did at Princeton fusion experiment and SDX, and also the simulation that we have done. So just quick comparison with what's out there in terms of propulsion technology. So this technology is simultaneously powerful and provide high speeds compared to the electric propulsion, which kind of provide good fuel efficiency, but in terms of power is kind of weak. And the opposite side is the chemical propulsion, that it's actually not fuel efficient. So this kind of covered this good area. So vision and roadmap is that in the next couple of years, we are going to build a prototype only for propulsion based on the plasmoid reconnection for low power. So build a prototype. And in the meanwhile, we're also working on the fusion-powered plasmoid spacecraft for high power, very of a megawatt, more than megawatt energy. So short term, we have had federal grants, 1 year, short and very small grants. Also some government grants are also pending, but really for completing the design and building the prototype for propulsion using this concept, we need a few millions. And the team, of course, you're a very capable team with PPPL engineers and scientists, and also private companies. And so you can contact me if you're interested. Also, or Laurie Bakley from PPPL Tech Transfer Office with any questions and interest. And for more information about the concept, here is the paper that you can read more. So I am ready for questions now. Thank you for your attention.
All right, thank you very much, Fatima. So I know we've been working together quite a lot on this technology
yes,
to help
yeah, thank you.
to help move it on. I'm not to say anything about myself. I know I'm familiar kind of with what you're doing for next steps here to bring it out of the lab, but where do you see it going, and what's the best way to get this commercially used?
Yeah, so the short term is that build it at the lab, build a prototype, and of course with investment, with at least a few million investment to do that, and to prove. So proof of principle, we definitely have so much data in an SDX and simulation. Proof of concept, do that at the lab with external private investors, and from there test it and then go beyond. And that is 3 to 5 years. And that's not the stop. We want to also have fusion powered based on the plasma connection, because these objects are really interesting. They carry momentum and current, so you can also use them for confinement in fusion plasmas.
And when you talk about fusion power, are you thinking small scale, distributed energy, or is this for large scale fusion?
This is compact. So everything we are thinking in a space, and we're thinking about anything that can take us, to Mars in 90 days, a few months. So we're thinking very compact fusion design, and it's possible with this kind of plasmoid generation, because you can get hot, and the nice thing, you saw these soap bubbles, you can have it continuously, and that's the steady continuously. That's the goal, to have a quasi steady state operation for fusion power. Yeah, that's the next application of this technology. Yeah.
So you have the rockets and the spacecrafts, but also potentially distributed terrestrial applications as well.
Yes. So yes, exactly. So there are many applications for this. So the applications are a lot based on the nice thing is that it's adjustable. Everything is scalable, so you can use it based on low power to high power. You can have different applications for that. Yeah.
Excellent. Thank you very much, Fatima.
Thank you.
We have to move on. I see a few questions in the chat here. Please remember that we're on a slight delay, so try to get those posted early on in the talk. But if you posted these, please send me an email or Fatima an email directly, and we'll try to get you answers to those. Next up will be Professor Andrew Houck from the Department of Electrical and Computer Engineering, and he will be presenting a talk on new materials to extend the performance of quantum computers. Take it away, Andrew.
Hi, thanks for inviting me here. I'm Andrew Houck, and I'm going to be talking about the work that we've been doing to develop new types of materials for quantum computers. Quantum computers are the first kind of computer we've ever invented that can operate in a fundamentally new way and can solve seemingly impossible problems. But there are two real challenges to actually making quantum computers that can do something useful rather than just interesting and neat in an academic lab. The first is that quantum information, the way the world works at the sort of subatomic or microscopic level, is incredibly delicate, and errors creep into the system at very fast rates. And the second is that you actually need to build quite big systems in order to do problems that are actually of use and of interest. Now, for the early part of the 2000s, we were making incredible progress on what's called the coherence time of these qubits. It's how long that quantum information can live. And you can see that we were seeing something like exponential growth from a nanosecond up to about 100 microseconds in 2012, at which point that kind of progress stagnated. Now, the field has excelled in other ways since then. You see Google and IBM have computers with 50 to 100 qubits in them. You have startups like QCI that are doing amazing work actually developing quantum systems. So the scaling is going well, but the individual pieces still aren't good enough. One of the pieces of work that we are doing in our lab to tackle this problem is to try and look at the fundamental causes of these of this sort of short lifetime, and to try and find new material systems that can get around these kinds of issues. So how long should a qubit live? How long should quantum information live? In the world of superconducting qubits, we use superconducting metal. Superconductors are absolutely lossless, so we don't expect there to be any loss in the metal. We put these on pristine sapphire substrates, which is the best dielectric known to mankind. You expect this to also give us error rates that should be much longer. And indeed, if you dig into some old literature, you can find that the predicted coherence times should be at least 30 milliseconds, if not all the way up to a second. So why are we stuck at 100 microseconds if these bulk sapphire crystals are so good? Well, it turns out that Wolfgang Pauli had the answer many, many years ago, which is that God made the bulk, but the surface was invented by the devil. So these sapphire materials are fantastic in the bulk, but the surfaces of both the metal and the dielectrics aren't good enough. And you can see this in this rather complicated looking plot. What this is meant to show is that if surfaces are the problem, we should expect every coherence time for every device ever made to fall along one of these colored lines. And in this study that tries to pull data from all over the place, you see that this is pretty much true. This red line dominates describes almost all of the data that exists. So what limits us here? What is going on at the surfaces of the metal and of the sapphire that are limiting our problems? Well, you can use the tools of material science to actually take a closer look. So here's a picture of niobium, which is the material that many superconducting qubits are made of. At the surface of it is oxide. This is like the rust that grows on your iron. And it's quite bad for maintaining coherence. And if you look very closely at the interface between the sapphire and the niobium, you can see that there's this sort of garbled mess. It doesn't quite look like a crystal. At the bottom, you can see the individual atoms in the sapphire. They look beautiful. Things are relatively ordered up top, which is good, but this mess here at the interfaces is not very good. If you look more closely at the oxide, you can actually measure how thick it is. So going from left to right, you're going from top to bottom. This light blue color is the oxide. That being thick is very bad for the coherence of the system. But even worse is this big purple peak in the middle. This is oxide that is not stoichiometric. It's sort of a very messy and ill-defined kind of thing, which tends to be extraordinarily lossy. So working with Bob Cava and Natalie De Leon, we started thinking about other materials we could use in place of niobium and how we could develop a full process to build the kinds of quantum systems people need out of new material platforms. We settled on a tantalum approach. It turns out that growing tantalum films is difficult in the proper crystal structure, but we came up with a process that allows us to grow the right crystal form of tantalum. And you can start to look at these kinds of things that we were looking at before for these new tantalum films. So unlike the niobium films that are dominant throughout industry, you can see that the oxide layer becomes incredibly thin, which is quite likely to be good. And this sort of amorphous peak that goes between the oxide and the metal is nearly gone in these tantalum films. Moreover, if you look at the interface between the metal and the sapphire, things look absolutely ordered. And you can see this beautiful crystalline structure both in the metal and going directly down to the surface of the substrate. So we found a material system that allows us to address the kinds of interface and surface challenges that plague the field and lead to short coherence times that had been stagnated for so long at 100 microseconds. When you put this together and actually build quantum devices out of it, how long do things last? It turns out that that we can get devices that are up to 360 microseconds here. So over a third of a millisecond, a 3 times improvement over the state of the art. If we do this across many different devices, we can actually see that this improvement is robust. We've not, since we introduced this new material system, we've been able to achieve these kinds of coherence times across many different devices over many iterations. We've exported this process to many other academic groups around the country by teaching them how to grow these films. And everybody who's actually started doing this has seen corresponding improvements in the coherence of their devices. This is only just the start. This opened the door for a new systematic approach to materials discovery for transmons. As I said earlier in this talk, we still think we can get something that is many tens of milliseconds or even up to a second if we manage to improve things further. And we are continuing to use this robust process to search for new materials. But if we put everything on that plot that I showed at the beginning of the talk, every prior experiment is one of these gray points here at the bottom, and you can see they all follow a colored line. We've now sort of moved things systematically upwards from here. Every colored line is a factor of 2 improvement. Our initial IP on this, developing the tantalum process, was this tower of blue points that marched us north, a factor of 3 improvement. And now we've continued to push that and continue to push things closer and closer to occasionally achieving as much as a factor of 8 improvement over the state of the art. We think this general approach towards material discovery for quantum computing is incredibly promising, and expect very many new results to come in the near future. So thank you. I wanted to acknowledge the rather large team of students I had on this. This group of people did all of the materials growth and characterization as described in this paper, and there's a corresponding patent that we filed, and especially Bob Cava and Natalie De Leon, the other faculty members who I've been working with. Thank you, and I'm happy to take questions.
Drew. Thank you very much, Andrew. So hopefully many of you were able to attend the full quantum computing talk that was held earlier in the conference, where you and others discussed everything going on at Princeton, the fascinating collaborations that we have. And I hope that's available for everyone to check back in on. You know, all of this is, at some point, quantum computing has sounded kind of science fiction, and it seems like now we're really moving it towards something real. You know, what are the first real applications of the tech, and when do I have a quantum chip in my cell phone?
So I don't think you're ever going to have a quantum chip in your cell phone, because almost all of the computing power you use nowadays exists somewhere in the cloud. I think quantum computers are going to be the same, and suddenly certain things that you never knew would get faster when you use quantum technology. We already have quantum computers today that can do problems that are maybe not useful, but at least very hard to understand what they're doing with classical computers. So in very specialized problems, they can either outperform classical computers or at least be incredibly hard to simulate what they're doing. Now, that said, these are not problems that are of particular interest. So I think what we'll see over the next decade is, as these systems get more available to people, we will start to see how much they can do on near-term problems like optimization, and then in longer-term areas like quantum simulation, potentially for things like chemistry or possibly for pharmaceuticals. You know, there are many algorithms around the world of cryptography.
Thank you. Let's see, nothing from the chat yet. Maybe you could just talk, you know, you're continuing to explore new materials here. You know, where are the next advancements coming from? Are you generating, you know, brand new substances? You're testing things that exist commercially?
I mean, I think it's a full range of things. So I think the core idea is to understand specifically what is causing problems. Then we can try entirely new materials. We can try and grow materials that haven't been used before. We can try and purify and find ways to passivate materials that exist. We can try and invent entirely new types of qubits that are actually immune to the types of noise you see here. So it's a full panel approach to all of the possible ways to fight this noise.
All right, thank you very much, Andrew. We will keep on here with our next presenter, which is Professor Ruby Lee from the Department of Electrical Engineering and Computer Engineering, and she will be presenting on a tiny AI module to detect smartphone theft and anomalous behavior. Take it away, Ruby.
Thank you. It's a pleasure to be here with you today. My overall research goal is to improve the security of computer systems, and this includes computing devices like smartphones. So we want to be able to prevent attacks, if possible, proactively. And if we cannot prevent an attack, then we want to be able to detect it as early as possible to prevent severe damage. So, for example, there are some new attacks that we know nothing about and have never seen, and they are called zero-day attacks. Well, we also want to be able to detect such attacks. Now, how can you do this when you know nothing about the attack and there's so many attacks and there's so many scenarios? Is there a way to do this effectively and efficiently? So our approach has been to use artificial intelligence to try to characterize the normal behavior of a system or of a user, and then to distinguish anomalous behavior from the characterization of normal behavior. So let me give you a practical, concrete example, which is with regard to smartphones. So we all use our smartphones all the time, and we carry it, with us all the time, and we store a lot of our important and sensitive information in it. The last thing we want is for someone to have access to our sensitive and secret information. But what do we do if the smartphone is stolen? So a smartphone imposter is someone who pretends to be the legitimate user. Now, if we are to defend against smartphone imposters, we must defend against the most powerful kind of attackers, which are those which even knows the legitimate user's pins and passwords. Now, if the attacker knows your pins and passwords, he can essentially pretend to be you. So what can we do about this? Well, what we've decided to do is to detect the anomalous usage of the smartphone through intrinsic movements of a user. So it turns out that the way we walk and the way we hold our smartphones as we use it and the way we move our arms, these are different from one person to another. So fortuitously, the smartphone has many sensors built into it, including motion sensors like the accelerometer and gyroscope. So the accelerometer measures large body motions, including walking and moving of arms and legs, so forth. And the gyroscope measures fine motor movements, like the way you hold your smartphone when you type into it or select items or rotate the smartphone or take photos or talk on the phone. So we will use the accelerometer and gyroscope as behavioral markers for the normal behavior of a user. And we've designed a tiny hardware module that can be built into a smartphone to automatically detect whether it is really you, the legitimate user, or not you, who could be an imposter. We call this SID for Smartphone Imposter Detector. So I've talked to you about what and why SID is. Now, let me briefly describe how it works. So as I said, the way people walk and move and hold their smartphones and use it apparently is different from one person to another. So you need to select behavioral markers, and we've selected the accelerometer and gyroscope. The next thing you have to do is you have to have an artificial intelligence algorithm that can use these behavioral markers and build a model of normal behavioral patterns, okay? In this case, it's of the user's intrinsic motions that he's not even aware of, okay? We sometimes call these behavioral biometrics. as distinct from physiological biometrics like your eye print or fingerprint and so forth. Okay, so it turns out that just deep learning itself is not enough. Even with like recurrent neural networks, which remember some of the past history of the motions, we also need to use statistical tests in order to determine whether it is normal behavior or abnormal behavior. So we use these methods in order to detect anomalous behavior. Now, in addition, we have built it into a tiny hardware module because we want this smartphone imposter detection to be done inconspicuously. It does not affect the user's usage of the smartphone at all. In fact, all his other applications will perform as normal, as usual, and he wouldn't even know that this smartphone detection, imposter detection is going on. And as an independent standalone module, it is also one with a smaller attack surface. It doesn't have software that is easily attacked or networking and interconnections, which are also more easily attacked than a hardware module, okay, which is harder to attack. And then it can run continuously, like every time you use a smartphone or when you are moving the smartphone, walking with it in your pocket, etc. And then we have designed it with smart architectural features so that it is tiny, has a very tiny footprint, low power. It can go into your smartphone and other small devices. And the idea, the end result, is that here is something that is tiny and low power and it's flexible because you can implement different algorithms on it. And it is something that gives you a smartphone that recognizes its owner. Imagine a smartphone that recognizes its owner and will only perform and give access to sensitive data to its owner. Okay. Now, it turns out that this smartphone imposter detector, or the method and the architecture that we have designed, goes far beyond smartphones. Okay, it can be used in all kinds of other scenarios. So let me give you an example of a really different scenario, which is like a power grid system. You know that the power grid system, of course, is a critical infrastructure. And what we've done is we've been able to detect anomalous behavior in the power grid system very quickly. And the earlier detection comes, the better chance we have of preventing further damage or serious damage. So how do we do this? Well, power grid systems have controllers, which are really just little computers, which control the actuators, which control the rest of the physical system. And these controllers can have a normal behavioral pattern. Now, of course, now the behavioral markers are different. Now we use hardware event counters, which essentially can be used to characterize the hardware and the software running on it. Rather than motion sensors as we did for the smartphone imposter detector, which was detecting human users. But anyway, using these different behavioral markers, but the same methodology and similar hardware, we can very accurately determine anomalous behavior in the power grid system. In fact, the accuracy is too good to be true. No false positives and no false negatives, with like 99% accuracy. So what then have we got? We've got a general purpose anomaly detector. It's tiny and small, standalone. It can go into any user device, IoT, controller of important critical infrastructures like the power grid or water treatment systems or what have you, or into other cyber-physical systems, into medical devices, drones, etc. So imagine the possibilities, a general purpose anomaly detector that you can put into any computer or device that can immediately detect anomalous behavior and thus potential attacks. So we would love to help you improve your systems if you would like to use our technology. Thank you.
Thank you very much, Ruby. I think we have time for one quick question here. I'll maybe combine two. One is, why did you make this a separate chip? Why not combine this in with the phone's existing hardware and make it a program, in with the iOS? And then to add on to that, we had an audience member ask, will this be an app? So maybe you can address both of those.
Okay, so we decided to make it a standalone imposter detector or a standalone anomaly detector because we don't want to impact the normal functioning of the system. So we don't want this imposter detector to not run as a program if there's other programs taking up all the running time of the machine. Okay, that would impact the detection, and we don't want to run the smartphone detector and make other applications run slower or not as well. And secondly, as I said, we wanted a smaller attack surface. It's harder to attack hardware and much easier to attack software. Now, can this be made into an app? Well, actually, of course, it can be made into app, but that will have the disadvantages I just mentioned. Now, you could make it software running on a standalone little processor, okay? It's standalone general purpose microcontroller that doesn't do anything else and, doesn't run anything else. But then, our smartphone imposter detector is about one order of magnitude smaller in size and power usage, and probably, that much better in flexibility and performance as well. I hope that answers both questions.
I think it does. Basically, I'll be downloading this in a year, right? I think that's all the time we have. So thank you very much, Ruby. And we will move on to our last but not least speaker, Professor Adam Finkelstein from the Department of Computer Science. And he will be joined with his graduate student, Jiaqi Su. And they will be talking about an AI to provide clearer audio for podcasts and video voiceovers. Take it away, Adam and Jiaqi.
Hi, everyone. I'm Adam Finkelstein, and as Chris mentioned, I'll be presenting this work along with Jiaqi, who's here in the room, and we'll join the talk shortly. Thanks to the CPI organizers and to Chris and the speakers in the session, Bruce, Fatima, and Andrew and Ruby. I really enjoyed hearing about your various projects. We're going to be talking about studio quality speech enhancement. We use audio for all kinds of purposes in our daily lives. This includes, of course, telephony, video conferencing, including meetings like this one, video logs, blogs, podcasts, audiobooks, and so forth. And people record audio in all kinds of situations, and there are a variety of acoustic factors that can reduce audio quality. One obvious factor is background noise, including the general environment where the recording is made, but it could also include subtle elements like air conditioners, computer fans, even a clock ticking in the room. Moreover, when sound travels from a speaker to a listener or to a microphone, it follows many different paths, and they have different lengths. And the speed of sound is actually relatively slow, so what arrives at the listener is actually many copies of the original sound with slightly different delays, which leads to a murky sound quality. And we call this reverberation or reverb. It's most noticeable in large echoey chambers, but it happens even in small rooms like this one. In addition, the microphone itself introduces its own effect that we call spectral distortion. People use all different kinds of devices with various trade-offs in price and size, engineering, that can impact the quality of a recording. And finally, digital representations of audio capture a sound recording as a series of pressure measurements recorded over time. And you need to record tens of thousands of them per second for high fidelity reproduction. However, for efficiency in both recording and transmission, various setups will limit the range of frequencies that can be transmitted. Now, human hearing extends to about 20 kilohertz, but traditional telephony restricted the bandwidth to less than 4 kilohertz, which is why our voices typically sound incomplete over the phone. So in short, real-world recordings that are captured in natural spaces with consumer-grade devices suffer from a variety of environmental effects that include noise, reverberation, distortion, and also suffer from limited bandwidth. So I'm going to, as an example, play a recording from a TED Talk, and you'll hear in it that there is heavy reverb and some background noise due to the environment where it was recorded. So here's that recording.
Right.
Let me try again. Here's
Writing books is my profession, but it's more than that, of course. It is also my great lifelong love and fascination.
Okay. So what we'd like to do is take a recording like that and process it and convert it into a recording that says the same thing, but sounded as if it had been recorded in a studio. So I'm going to play here the output of a system that we've been working on that hopefully cleans up this sound.
Writing books is my profession, but it's more than that, of course. It is also my great lifelong love and fascination.
Okay, so hopefully that sounds better to you. It certainly would help if you're listening to it with headphones. To do this, we rely on a computational model that is called neural networks that mimics the interconnected architecture of neurons in the human brain. And in a moment, I'm going to pass the microphone to Jiaqi, who's going to say a little bit more about how we train these networks.
Hello, everyone. I'm Jiaqi. So I'm going to talk more about the details of our approach. So our training process actually relies on two neural networks in a learning framework called generative adversarial networks. It has been hugely impactful in areas like computer vision, but it's only recently gaining significant traction for audio processing. The first network is called the generator, and its job is taking a real-world recording and output a cleaned-up version of the recording that hopefully sounds as if it was recorded in a studio. The other network is called the discriminator. Its job is to examine a recording and determine whether it was cleaned up by our method or if it's actually recorded in a real studio. The two neural networks are trained together as adversaries battling with each other. Each one forces the other one to improve as they learn. Once training is complete, we can discard the discriminator, and the generator is what we use for cleaning up audio. One subtle aspect of the training process is about the training data. We actually need example recording pairs, one from a real-world setting and another one from a studio setting, where they should contain the same speech content, meaning same speaker saying same things. There exists a few real-world data sets like this, but of limited scale. For example, the device and produced speech dataset. However, for our training purpose, we need literally millions of example pairs, and such data is expensive and time-consuming to record. Therefore, we rely on a different strategy involving simulation. So we can start from a studio quality recording and then synthetically add noise, reverb, and distortion, as well as restrict its bandwidth. The input and output of this process gives us an example pair that has same content. Moreover, we can combine those effects in many different ways to produce the millions of examples we need for training our neural networks. In the experiments, we performed many listening tests involving thousands of people via a crowdsourcing platform called Amazon Mechanical Turk. Most of those experiments were comparing the results of our approach to those of other state-of-the-art methods, as well as to actual studio recordings. So one high-level takeaway here is that the recording cleaned up by our method is often difficult for people to distinguish from actual studio recordings. So this shows the quality of our result is on par with actual studio quality. Of course, as Adam mentioned, there are many direct applications for this work, such as enhancing home recordings for podcasts. In addition, it can be applied to other audio processing tasks, such as text-to-speech, voice conversion, and so forth. This ends our talk, and thanks very much for everyone for listening. We welcome questions now. Also, if you prefer to follow up with our work later, our emails are shown here.
Thank you very much, Adam and Jiaqi. So I had one question for you. How do you balance the algorithm between making one characteristic voice, maybe mine a very baritone voice versus a higher frequency voice? Are you focused on making one person's voice better or broadly making all of them?
I think so. Our algorithm is mostly making like all kinds of different voices, like making all of them sound better. But one thing, like you mentioned, the specific application of improving one specific one person's voice is definitely one interesting application that can be further we can further adapt our approach on such application to make your voice sound perfect in all kinds of scenarios.
Could this possibly improve the ability of home assistant devices to recognize what you're saying?
Yeah, I think that's definitely a very interesting application, and we can basically based on maybe a few minutes of recording of your voice, maybe we can improve our algorithm and adapt our algorithm to your voice, so that you can use in like a home assistant setting, like personalized enhancement. Yeah.
Gotcha. Does this kind of? Oh, sorry. Go on, Adam.
Oh, I was just going to say, riffing on your two questions together, maybe we could adapt a personalized voice improvement system that works specifically for your phone, for example, so that your phone knows how to enhance your voice specifically for transmission.
That kind of ties into an audience question I have, which is, what are the applications? Where do you see this going next?
Well, an obvious application would be for any kind of recording software where you are making, like, for example, a video log or a blog, video editing software. It's often the case that people will record something and then edit it later, and it would be very nice to have a button that you could click in that software that just says, make my recorded voice sound better before I post it on YouTube or wherever I'm posting it.
And one more quick one. Someone mentioned they thought they recognized the street from your picture being Ottawa, and was that correct?
We're not sure where the picture came from, unfortunately. It came from, as far as we know, from the internet.
Maybe now from Ontario, Canada. So thank you again to both Adam and Jiaqi and all of the presenters in the tech track, as well as all of the presenters that we've had during Celebrate Princeton Innovation as a whole. And I think that will conclude here the research portion of our presentation. And I will pass the mic off to my boss, the Director of Technology Licensing, John Ritter. Take it away, John.
Thank you, Chris. Good evening, everyone. My name is John Ritter, and I'm the Director of the Office of Technology Licensing here at Princeton University. On behalf of the entire Office of the Dean for Research, we want to thank you all for participating in Engage 2021 and celebrate Princeton Innovation. Princeton is committed to developing a robust and inclusive innovation ecosystem, not only among our faculty and researchers, but more broadly in the region. We hope that all of the discussions over the past few days will encourage you to reach out to me, any of the researchers, or any of my colleagues with additional questions or for further information. It is only with your assistance that we can continue to be successful in translating ideas from academic basic research into products and services that can benefit humankind. Have a good night and be well.